I'm Taihei Oki from University of Tokyo. I start my talk, which is titled On Solving Non-Commutative Weighted Edmonds Problem. This is a summary of my talk. I proposed a simple polynomial time reduction of commutative or non-commutative weighted Edmonds problem to commutative or non-commutative unweighted Edmonds problem. This is the contents. First, I talk about Edmonds problem. Okay, let K be a commutative field and x1 to xm be commutative symbols. A linear symbolic matrix, or simply a linear matrix over a field K, is a matrix in this form. Here, B0, B1 to Bm is an n times n dash matrix over K, and x1 and xm are commutative symbols. V is the matrix. Linear symbolic matrix B is viewed as a matrix over the polynomial ring over K and indeterminates x1 to xm, or field of fractions called the rational function field. The Edmonds problem, or commutative Edmonds problem, which was introduced by Edmonds in 1967, is as follows. In this problem, we were given a linear matrix B over a field K in M symbols, and what we do is to compute the rank of B. We can solve this problem by simply randomly substituting random values into the x1 to xm. But, however, no deterministic polynomial time algorithm has been not known. So it is known that if there exists such an algorithm, then a very non-trivial theorem holds on circuit complexity. In some situations, an efficient deterministic polynomial time algorithm was obtained from the viewpoint of combinatorial optimization. So, for example, if every quotient matrix Bi has only one non-zero entry, then the Edmonds problem is just a bipartite matching. And also, if every Bi is of rank 1, then the Edmonds problem is equivalent to the linear matrix intersection problem. And if every Bi is skew symmetric and has only two non-zero entries, the matrix B is called Tat matrix of a graph in this situation. And the computation of its rank corresponds to computing the maximum size of a matching. And if every Bi is skew symmetric and of rank 2, then the Edmonds problem is equivalent to the linear matrix parity problem. The commutative setting is very easy to understand, but hard to solve deterministically. Recently, the non-commutative version of Edmonds' problem is hot topic. I explain the non-commutative Edmonds problem. Let K be a field, and let x1 to xn be a pairwise non-commutative symbols. The NC linear matrix, non-commutative linear matrix over a field K is a matrix B in this form, where B0 to Bm are matrices over K. The matrix B here is viewed as a matrix over the polynomial ring in K, polynomial ring K bracket x1 to xm in non-commutative symbols. This is a non-commutative ring, and or its skew field of fractions called free skew field. Here, skew field is a division ring. So NC non-commutative Edmonds problem is as follows. In NC Edmonds problem, we are given a non-commutative linear matrix B, and then we want to compute its rank. Here, the rank of an NC linear matrix, which has non-commutative entries, is defined as follows. There are two equivalent definitions. The first one is the rank of B is defined at the minimum R such that B can be decomposed into the product of two matrices of size if B is n times m, then the first left matrix, green matrix, is n times r, and the right matrix is r times n. And an equivalent definition is the rank of B is defined as the maximum of R such that B has a non-singular submatrix of size R. Here, non-singularity is just invertibility. Indeed, this non-commutative Edmonds problem is deterministically polynomial time solvable. If the base field K is the Q, which is the field of rational numbers, an operator scaling algorithm is known, and if K is a general field, then an algorithm called Wong's sequence and the cat-zero relaxation provides a deterministic polynomial time algorithm. And in addition, operator scaling algorithm and Wong sequence algorithms for K is Q run in time polynomial in the input bit length. Yeah, so very nice algorithms. And this is the end of the first section. In the next section, I talk about weighted version of Edmonds problem. Okay, I introduce linear polynomial matrices. Let K be a field again, and I first talk about commutative setting. Let x1 to xn be commutative symbols, and let also I introduce an extra symbol, indeterminate S. Here S is also commutative. Commutes with any element in K and x1 to xn. A linear polynomial time matrix over K is a matrix A, which is written in this form. So this in this matrix, each entry of this matrix is a polynomial in S, and also each coefficient matrix A0 to AL are a linear matrix over K. Here, the matrix A is viewed as a matrix over the polynomial ring f of S. Here, f is k power n x1 to xn, or over the rational function field fs. The weighted Edmonds problem, or commutative weighted Edmonds problem, is as follows. We are given a square linear polynomial matrix A, and then we want to compute the degree of the determinant of A. Here, we need to say that the determinant of A is a single polynomial in S itself, so its degree in S is well defined. So, one question is, why is this problem is called weighted? This is based on the connection of this between this problem and the weighted matching in the combinatorial optimization. Here, okay, first, suppose that we are given a bipartite graph like this, then we construct a matrix B. Here, each row of this matrix corresponds to each left or blue vertex, and each column of this matrix corresponds to each right vertex. And if the each entry of V corresponds to an edge of and pair of the left vertex and the right vertex of the bipartite graph, and if there is an edge for connecting its pair, then we set distinct indeterminate uh, in the entry. Okay. Then, it is well known from the definition of the determinant that the maximum size of a matching of this bipartite graph is equal to the rank of this matrix B. Then, how about the weighted version of this bipartite matching problem? In the weighted bipartite matching, we are given a bipartite graph as well as an edge weight, like this. Then, we construct a polynomial matrix A, like this. In this polynomial matrix, so S, we introduced symbol S, and we set the weight of each edge as the power of S in each entry, in the corresponding entry of A. So for example, the 1 entry of A is x11 times S squared. This square, the 2 in the exponent of S, corresponds to the weight of the corresponding edge. Then, it is also known that the maximum weight of a perfect matching of this bipartite graph is equal to the degree in S of the determinant of A. So, in this sense, the computation of the degree of the determinant of a polynomial matrix corresponds to an weighted version of the Edmonds problem. Okay, indeed, some instances, some special cases of commutative weighted Edmonds problem can be solved by reducing it to the weighted combinatorial optimization problems as the unweighted case. So for example, if every coefficient matrix has only one non-zero entry, then the weighted Edmonds problem corresponds to the weighted bipartite matching, and so on. So there, simple extension of the correspondence between the Edmonds problem and the combinatorial optimization problem in the unweighted case to our weighted case. Yeah. So then, but of course, the solving weighted problem is harder than solving unweighted problem. So on commutative case, it is difficult to design a deterministic polynomial time algorithm for weighted Edmonds problem, because the unweighted problem is also difficult as well. So it is natural to consider the non-commutative weighted Edmonds problem. Okay, I introduce it. Okay, let K be a field again, and let x1 to xm be pairwise non-commutative symbols. And also I introduce an extra symbol S. Here we assume that x1 to xm are pairwise non-commutative, but S commutes with any element in K, and x1 to with x1 to xm. Okay, then an NC linear polynomial matrix over K is a matrix A in this form. This is a simple extension, natural extension, where each A coefficient matrix AD is an NC linear matrix over K. Okay, then A is viewed as a matrix over the polynomial ring Fs or over the L-versional function field Fs. Here, F is the free skew field over K in x1 to xn. Then, the non-commutative weighted Edmonds problem, which was introduced by Hirai, is as follows. We are given a square non-commutative linear polynomial matrix A, and we want to compute the degree of the determinant of A. But it should be noted that A has non-commutative entries, so defining the determinant of A is non-trivial task. Indeed, here we employ the Dieudonné determinant as determinant of A here. The Dieudonné determinant is a generalization of the usual determinant to matrices over skew fields. Its definition, to introduce its definition, I need to introduce some ring theoretic notions. So I don't want to do it, but defining the degree of the Dieudonné determinant is much easier. So I define the degree of the Dieudonné determinant here. If when we are given a matrix A over a skew field, then A can be decomposed into the sequence of 4 matrices. The first one is lower unitriangular. Here, unitriangular is a triangular matrix whose diagonal entries are all 1. And the next one is permutation matrix, and the third one is a diagonal matrix, and the last one is an upper unitriangular matrix. Then, if A is a matrix over commutative field, then its degree of the determinant is just a sum of the degrees of the diagonal entries in the diagonal matrix. We employ this as the definition of the degree of the Dieudonné determinant for a matrix A over skew fields. Yeah, this decomposition is called Burat decomposition. And the important thing is, indeed, this problem is deterministically polynomial time solvable. Yeah, which was proved by Hirai. In this algorithm, we solve the non-commutative Edmonds problem iteratively. Here, polynomial term is in terms of the number of arithmetic operations over k. And indeed, there is no bit length guarantee for k or q, for the case of k or q. Okay. Okay, I talk about my proposed reduction in the remaining time. Okay, suppose that let F be a field K of x1 to xm or a free skew field. And we are given a commutative or non-commutative linear polynomial matrix A. And we consider the following matrix instead of the input. We multiply s to the minus L, then we obtain a polynomial matrix in S inverse. If you are given a polynomial matrix and S inverse, we construct an expanded matrix like this block matrix. It is easy to confirm that this expanded matrix is commutative or non-commutative linear matrix over K. And if K is Q, then the bit length of this matrix is polynomially bounded. And also, we can show that this matrix is multiplicative. That is, omega mu of LB is equal to the omega mu of A times omega mu of B. Okay, then this is a very important theorem in my reduction. Let dk of A be the maximum of the degree of the Dieudonné determinant of a submatrix of A of size k, and let omega mu of A be the rank of capital omega mu of A. Then, indeed, we have shown that the sequence d0 to dr, here r is the rank of A, is a concave integer sequence, and the sequence omega 0 to omega 1, omega 2, blah, 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 is a convex integer sequence. In addition, they satisfy these equalities. This is called the Legendre Conjugacy. This result generalizes that of for matrix spaces over fields. To show this conjugacy, we use the Smith-McMillan form of matrix. Okay, a matrix A over F of S is called proper if the degree of all entries are non-positive, and A is called biproper if it is proper non-singular and its inverse is also proper. Then it can be shown that for any matrix A of over Fs, there exist biproper matrices S and T and integers, non-positive integers, alpha 1 to alpha r. Here r is the rank of A, such that SAT is a diagonal matrix whose the diagonal entries are S to the alpha 1 to the S to the alpha r. This is called the Smith-McMillan form of A. Okay, then by using the Smith-McMillan form, the exponents of the Smith-McMillan form alpha 1 to alpha r, and the quantity nd, which is obtained from the alpha 1, alpha i's, we can show these relations between d and omega. So intuitively, this relation connects dk and mu omega through the Smith-McMillan form. Using these equalities, we showed the Legendre conjugacy between dk and mu omega mu. In the Legendre conjugacy, the dk of A is obtained by the minimum of the omega mu of A minus k mu. So to compute the dk of A, it suffices to compute the minimum value of this quantity in the right-hand side. Here, the objective function of this minimization is a discrete convex function. So we can compute its minimum value just by the standard binary search and rank computation of omega mu of A. Here, omega mu of A is a commutative or non-commutative linear matrix. So we can compute the value of the objective function just by solving the unweighted commutative or non-commutative Edmonds problem. So our main theorem is that commutative or non-commutative weighted Edmonds problem can be deterministically reduced to commutative or non-commutative Edmonds problem with matrix size Ln square. In addition, when k is q, this reduction retains the input bit length. Okay, this is a summary of this talk. Thank you for attention.